Deriving rules for exponents. We'll be deriving the rule for zero and negative exponents as well as the quotient rule. For our terminology, a power is an expression represented by a base number being raised to an exponent. The base is the number that's being raised to the exponent, and an exponent is the number in an expression that tells how many times a base is to be used as a factor. So here's an example. 2 to the 5th is a power, and the base is 2 and the exponent is 5. To evaluate it, we multiply 2 by itself 5 times. 2 to the 5th equals 32. So we'll get practice evaluating powers now. First, we'll start with the powers of 2, which are very important. That we could start to even memorize these would be good. And then, just like powers of 2, we could also consider the powers of 3 and the powers of 5. So then we might want to start generalizing rules. So what if we wanted to consider any number raised to the first power? We can look at all the numbers here raised to the first power and generalize any number raised to the first power equals itself. Next, we could look at any number raised to the 0 power. And we could generalize that any number raised to the 0 power equals 1. Now, numbers raised to the negative 1 power. Any number raised to the negative 1 power can be written as 1 over itself. So n to the negative 2, a number raised to the negative 2 power can be written as 1 over itself squared. So now we can simplify some expressions. We can rewrite x to the negative 3 as 1 over x cubed. In the next expression, it's the negative exponent that we want to represent in a positive way by changing its place in the fraction. So this expression becomes 1 over x squared y to the 4th. And in the last expression, to make that negative exponent positive, we can change its place in the fraction and bring it up to the numerator. So 1 over w to the negative 4th is the same thing as w to the 4th. So let's evaluate some expressions here. If a is negative 2 and b is negative 3, then we can substitute into the expression, and this equals 4 times 1, which is 4. Now in the next expression, only b is being squared. So it's important that we pay attention to the fact that it's negative 3 times negative 3. This final answer will be negative 81. Now the quotient property of exponents. So let's see if we can make sense of an expression like x to the 7th over x to the 3rd. The numerator would have x being multiplied by itself 7 times, and the denominator x is multiplied by itself 3 times. So we can cancel out those 3 x's in both the numerator and denominator because they divide to equal 1. And this expression becomes x to the 4th. Now, let's take a look here. We have a negative exponent in the denominator, so we can rewrite it this way. And that's going to become x to the 10th. And now let's look more closely at these exponents. 7 minus 3 equals 4, which is exactly the exponent we ended up with. 3 minus negative 7 equals 10. So the quotient rule, or quotient property, would say x to the m divided by x to the n equals x to the m minus n. Now let's apply this quotient rule. We'll have, for the x's, x to the negative 5 minus 1 times y to the 6 minus 2 times z to the 1 minus negative 3. Now we can simplify the exponents, and that negative exponent of x, will put that down in the denominator to make it positive. And so we have simplified the original expression, and we use the quotient rule. Now we'll take a look at another example, and we'll apply what we know about negative exponents. I can see that the x to the negative 5th could come down to the denominator, and the z to the negative 3rd could come up to the numerator. And now to simplify this, it's easier to simplify with positive exponents